Hello everyone, my name is Qitong Wang. Today I will share with you some introductions to our ML systems project. First, this project is about how we can efficiently train neural networks. And one observation that we made is that now we have larger and larger models, and the scale of the models is increasing exponentially, but the memory size of our GPU devices is only increasing linearly. So memory is actually becoming the bottleneck when we do machine learning training. And let's just quickly get to briefly give you an introduction on how to train a neural network. Here, assuming that we just use this F to denote the neural network as a black box model, and then having the input X and the label Y true, and then our network can predict the Y, which is we denote as predict. And then with this Y true and Y predict, we can then compare how far away they are from each other, and then get the loss value, which is how far away, how worse, how badly our network is now. This is called the forward pass. And with this loss value, and then we can, like using these differences, we can get to know how we can update parameters in our neural network. And this is called the backward pass. And then the way how we update our parameters is using the gradients of the loss functions with regard to each weight. So let's get down to some notations. So here, this is the forward pass. If we just taken like one very simple NLP, 2 layers NLP as example here. So here, like when we do unbox this black box FX model, this F function, so what we do is that actually we do a function composition and decomposition. So what is function composition? So function composition is, for example, y equals fx and then z equals gy. So y is a function of x and z is a function of y. Then you can chain these two functions together to make z a function of x. So here is that like if we consider this as end-to-end, then we can think about like z is first like z1 is a function of s, but if we chain all of this together, z4 is also a function of s. And why this matters? This matters because using this chain rule, we can then get the derivatives, which are the gradients of the loss function with regard to each of these parameters and input values. And so after we get all the parameters, all the gradients, then we can get to know how we can update each parameters in this neural network, which is shown in this graph. And this is, so on the left is the computational graph when we do the forward path, and on the right is computational graph when we do the backward path. So in details, so this delta Z1, we call them gradient maps. So basically they are the gradients that we use to calculate in the backward path. And they are calculated in the backward path. They are consumed immediately after they're calculated. And then they're only used in backward path. And then this Z4, Z1, Z2, Z3, we call them activations or latent feature maps. They are calculated in the forward path, but they are used in the backward path. And then this W are the parameters of the neural network. And so they are, we use them in the forward path to calculate the values, but they will be updated in the backward path. And last, so this delta W1 are the gradients of the weights, which are also generated and used in the backward path only. So now we know that actually we have 4 different types of memory that we use in the backward and forward path. If we break them down, actually, so we can show that actually the feature maps is the main consumer of the memory of the GPU memory in GPU training. So now the question comes down to how we can reduce the memory footprint in the GPU training. So apparently we need to start with the bottleneck, which is the main consumer of the memories, which are the feature maps. And one way to do this is it's called activation checkpointing. And here still like we get like more in-depth demonstration of how the feature maps are generated and saved in memory during training during one forward pass and backwards training. And then we show what is activation checkpointing and how it can be used, how it can help us to reduce GPU memory. So here still like given G input X and parameter W1, we can generate Z1 from X and W1. And then after we generate Z1, since we will need it in the backward pass, we save it in GPU memory. And so on and so forth, we come to Z2, Z3, Z4, and Z5. And with Z5, we can call this the loss function. And then this finishes our forward pass. And then now we start our backward path. With a loss function and Z5, we can calculate delta Z5 and then delta W5, which are the gradients of the W5. To calculate the gradients of W5, we need D4 and delta D5. And then after we have the gradients of W5, we can update W5. And then we can delete all of them like in memory because we finished using them. And so on and so forth, we can calculate the gradients of W4 and update W4 and then remove Z3 because it is only used to calculate delta W4. And then we calculate delta W3, update W3, and then remove Z2 from GPU memory. And then we calculate W2 and update W2 and then we can remove Z1 from GPU memory. And so on and so forth. Now we can now we finish updating all the parameters in the backward path. Also we finish we used all the activation maps that we saved in the forward path and now we can see that actually the consumption of GPU memory is not the same over time. It is increasing in the forward path and then it is decreasing in the backward path. So this is there actually a peak, and the peak of this, so the peak of this trend, the peak of this GPU memory consumption reaches peak at when we calculate the loss function in the end of the forward path, and then start to reduce with starting of the backward path. So what is activation function? So what is activation checkpointing? So activation checkpointing means that we don't save these activation maps in GPU memory. We selectively discard some of them in GPU memory, and then when we need the activation maps that we saved in GPU memory, we trace back to calculate this. We trace back to whatever we have in GPU memory, and then we calculate these activations using the inputs that we have. So what does this mean? So let's also have a live demo here. So still like now we're starting to calculate Z1, and then using Z1 we can calculate Z2, and then after we calculate Z2, so we will no longer use Z1 in the forward path, and we can delete Z1, just remove it, and then with Z2 we can calculate Z3. And then after we calculate Z3, similarly, we no longer need Z2 in the forward path, then we can remove it from GPU memory. And so on and so forth, we got Z4, and we got Z5, and we can select to preserve Z3 in GPU memory and remove Z4 as well. And now, instead of have 5 tensors in your GPU memory, we only got 2 tensors. So this highly reduces the peak memory consumption of our training workflow. And then, okay, so now we start the backward path with loss value because we have Z5, and now we can update W5. Now the problem is that like when we Now it's L, so we can calculate with L, and then we need to calculate the gradients of W5. To calculate the gradient of W5, we need Z4, but actually we deleted Z4 from GP memory. And then if you check the computation graph, how we get Z4, we only use Z3 and W4. And then, so in this part, to calculate Z4, we can actually use Z3 and W4 to recalculate Z4 and bring it back to GP memory, and then use it to calculate the gradients of W5. And then we got it, and then we delete the numerator, of course. And then, so to calculate the gradients of W4, we have these three. We directly do it, and we got Z4. And now going on, so we need to calculate the gradients of W3, but here actually we need Z2, but we don't have Z2, right? And we want to recalculate Z2. How can we do that? We go back to check. To calculate Z2, we need Z1 and W2. So W2 is in GP memory, but Z1 is not. We also need to calculate Z1. And then to calculate Z1, we need X as our inputs and W1. So we get our inputs and get W1, and we use these two to get Z1. And with Z1, we calculate Z2. And then now we have Z2, we can update W3. And after we update W3, we continue to update W2, and then finishes. So we can say that actually, so in this version with activation checkpointing, you only save at any time, you only save 2 tensors in GP memory. So this largely reduces the peak memory consumption of our training workflow. But so what is cost? We pay a little bit cost by recalculate the tensors that we need in the backward path. But because we largely reduce our peak memory consumption, actually we can accommodate more batches, larger batch sizes in GP memory when we do neural network training. So this can help us to improve the whole throughput when we do the training and hence reduce the training time, overall training time. So this is our machine learning system project. It can be divided into 3 steps. First, we need to construct and profile. We need to construct computational graphs on PyTorch, and then compile the memory consumption and runtime of the graph and each individual nodes. Second, we need to design the activation checkpointing algorithms that we described just now. So of course, like so your algorithm needs to be designed based on some observations, and you can get these observations from the Mu2 paper. And also it should be reflected in that you can actually get an improvement on the peak memory consumption and hence larger batch sizes. And last, we need to write the PyTorch computational graph to deploy the activation checkpointing algorithm, and such that we can experiment and see some effect of this activation checkpointing algorithm. And then, so to help you start, we provide a starter code, which you can find it in this link. And also we encourage you to check out this Mu2 paper. It's very thoroughly described the checkpointing technique. And also, if you have questions, just come to the lab. So basically, there is a mid-level check-in. So the goal is that we can finish phase 1 by the mid-level check-in. Phase 1 basically means that you should be able to construct the computational graph and profile the memory and time consumptions of each node and the graph. And then, like when you do mid-level check-in, we expect that you can come with a document with the following 2 experiments. The first one is that you can show us the statistics that you run and collected during experiments. And second, is we expect you to get the peak memory consumption, peak memory consumption peak memory consumptions versus the mini batch sizes without activation checkpointing. So we can use this as a baseline to compare with the version that we have with activation checkpointing. And in the finals, so we expect you to deliver your code, and this is fully runnable code, and you can explain what each block of the code did carefully and clearly. And then you can live demo your code, how it runs and how it improves to the TFs. And also, like, you expect it to deliver a document with the following experiments at least. So the first one, similar to the media check-in, is you can show us your computation graph and also profile the memory and time consumptions of this computation graph and these nodes. And then you can show your peak memory consumption figure versus mini batch sizes with and without activation checkpointing to show that how much improvement that your algorithm can bring to the new network training. And also, we expect you to show the activation latency versus the mini batch size performance bar. So which is that the cost, how much you pay by involving the activation checkpointing algorithm. And so let me also show you. So this is the starter code repo. And so we already create some instructions that how to kick off your project. And after you download this Git repo, so this is the main file that you should start with. You can see that we provide you some domain models, and you can as shown in the project document, you can use BERT, and also you can use weight as a model, and all the model that you need should be able to find in PyTorch. You don't really need another additional library to get the models. And also, yeah, if you run, you can start after you configure the environment, you can try to run with the starter code. Yeah, and then you should be able to see all these outputs. So here we also we printed the nodes individually, but also you can comment this out and then get the computational graph. This is the graph if you only compute the graph. And then you can start with understanding what this graph means. Like how, for example, you can try to navigate through the PyTorch document and check what this placeholder means. And here, what does number of users mean? And then here are the arguments. So what are the arguments? You can see that actually, so each of these variables are used later, for example, here. So this argument 0, 1 is used in this output, in this T, and it is used here. And then this is option. So this is the operator that uses this as input, uses I0, 1 as input, and so on and so forth. So you can check each operator. You can check each operator, and basically, so this start with this percentage is a variable. So basically, this T is the output of this operator. And similarly, this is not only an operator, but also it is a result of this operator. So on and so forth, so you can check all the operators, their meaning, and then analyze this graph, and then think about how you can do activation checkpointing to improve the peak memory consumption. And yeah, so this graph tracer, so this file is just is an infra file that we use to generate the figure and do some modification. So you don't feel need to do anything with this file, you can just use it. And then basically what you need to do is just need to modify this graph profile file. And then here you can see that in this file, there is a graph profiler, and then you need to you need to modify this graph to profile the computation graph. And then in the starter code, you can see this compile function. So you need to modify this compile function to translate from the old graph that you get from the model and then convert it to the new graph with activation and pointing and return it to be used in this function. So that's it. We hope you enjoy. Thank you.